As we gazed up at the heavens, we asked where we had come from, how all the stars were created, how all the elements were made, even how the universe itself had begun. One of mankind's greatest achievements is that we've answered these questions. What is truly remarkable is that this understanding has come through the study of the smallest building blocks of matter, atoms. As we peered inwards, we realized we could explain what we saw when we peered outwards. The atom has helped us solve the greatest mysteries of existence.
Everything in the world we see is made out of tiny objects called atoms. And yet we only proved their existence at the beginning of the 20th century. The first shock was to discover how small they were, less than a millionth of a millimetre across. There are trillions in a single grain of sand.
Amazingly, we now have a pretty good idea of the number of atoms in the known universe. Now, given the vastness of the universe and the minuteness of the atom, it's not surprising that this is a mind-numbingly huge number. It's 1 followed by over 70 zeros. That's a trillion, 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 trillion atoms. We don't only know the raw number of atoms in the cosmos, we also know that they come in 92 different flavors. These are called the elements, and you'll recognize many of them as familiar parts of the world around us. Oxygen, iron, carbon, tin, gold, and so on.
Everything in the universe, the stars, the planets, the mountains, the seas, the animals, you and me, we're all made of these atoms, or combinations of them.
It's an astonishing human achievement that we now know not only how many atoms there are in the universe and how many different types there are, but why they exist at all. We can now explain how every one of those trillion, 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 trillion atoms was created. It turns out that the answer to the mystery of creation itself lies within the heart of each and every atom in the universe.
The story of how we came to understand creation itself started over 100 years ago in a small laboratory in southeast Paris. This piece of paper is a remarkable artifact. It's from the notebook of the woman who first studied radioactivity, the chemist Marie Curie.
It's incredible, 100 years later, and this piece of paper is still spitting out radioactive particles. The photograph on the left shows the concentration of the radioactivity. You can actually see Marie Curie's thumbprints on it. But what's really incredible is the sheer power, the energy given off by radioactivity, that this piece of paper is still spitting out these particles 100 years later.
Still stuck to the paper are tiny but intensely radioactive particles of a substance that Marie Curie discovered in 1898, a substance she called radium. It was a sensational discovery for one primary reason. Though radium looks like an unremarkable grey metal, it contradicted all the then known laws of science. Because radium pumps out invisible yet powerful rays of energy, which could fog sealed photographic paper and burn human flesh. They're a little like radio waves, which is why Curie called radium radioactive. But the waves were millions of times more powerful than any radio wave previously encountered. Also, radium appeared to contain within it an inexhaustible store of energy. Curie worked out that a gram of radium, a piece much smaller than a penny, contains more energy than 100 tons of coal. By the turn of the century, the French public and the tabloid press were fascinated by radium. And rather touchingly, though no one had a clue what radioactivity really was, everyone assumed it must be wholesome and healthy.
When radium was first discovered, they found all sorts of weird and wonderful commercial uses for it. Here is the radium bath products. There's the radium eau de cologne, atomic perfume, and radium face cream. Apparently it enhances beauty through healthy skin. There's even the radium razor blade. I'm not quite sure how that's supposed to work. Ah, the good old days, clearly when ignorance really was bliss.
Whatever the public made of it, to the scientific community, radioactivity was just about the most exciting thing possible. The brightest minds of a generation clamoured to study it. And the price of radium, its most potent source, soared to thousands of pounds per ounce. And radioactivity didn't disappoint. In 1919, it produced its greatest revelation yet. A revelation that would ultimately lead to a fundamental understanding of the atomic world. The revelation was that radioactivity allowed humanity to fulfill an age-old dream: to become alchemists.
Alchemy, the power to change base metals into gold, the quest for the so-called philosopher's stone, which has the magical ability to transmute one substance into another, has been an obsession for centuries. It conjures up wonderful tales of sorcery and wizardry, as anyone who's read Harry Potter knows very well. The power and wealth that would surely come to anyone who mastered alchemy seduced many great scientists and thinkers, like Isaac Newton, Robert Boyle, and John Locke. All of them tried to change one element into another, and all of them failed.
Then, in 1919, the secret of alchemy, the mystery of the philosopher's stone, was finally revealed, not in a wizard's den, but in the physics department at Manchester University. The world's first true alchemist was Ernest Rutherford. A loud, straight-talking New Zealander, Rutherford had come to dominate the study of radioactivity. He had wonderful intuition and was fearlessly prepared to challenge conventional wisdom. And alchemy would require Ernest Rutherford to follow his intuition deep into the unknown.
The discovery was almost accidental. It began when one of Rutherford's students noticed that when radioactive materials like radium were placed inside a sealed container of ordinary air, mysteriously, small amounts of the gas hydrogen begin to appear. Now, this was bizarre. Ordinary air contains virtually no hydrogen, and yet, in the presence of radioactivity, it was appearing out of nowhere. This was precisely the kind of problem that Rutherford, now at the height of his powers as an experimental physicist, loved, and he flung himself at it. He began by isolating all the different gases that make up the air we breathe: nitrogen, oxygen, water vapor, and carbon dioxide, and studied how each of them behaved in the presence of radioactivity. And then, eureka! Rutherford realized that in the presence of powerful radioactive rays, the gas nitrogen, which makes up about 80% of the air we breathe, changes into two new substances: the gases oxygen and hydrogen. Then and there, Rutherford had transmuted one element into two others. He'd become an alchemist, and radium, with its powerful radioactivity, was the philosopher's stone.
The press hailed Rutherford as the first alchemist, but in fact that was the least of it. What alchemy had shown him was the inside, not just of the atom, but of the strange object at its centre, its tiny beating heart, the nucleus. To get a sense of this achievement, remember Rutherford and his contemporaries at Cambridge had only a sketchy idea of what an atom was, but they did have an idea of its size.
And it's mind-numbingly tiny, 1/10 of a millionth of a millimetre across. Let me put it another way. There are more atoms in a single glass of water than there are glasses of water in all the oceans of the world.
And Rutherford now also knew that the atom had structure, that within the atom there was a subatomic world. He pictured each atom like a tiny solar system. At its centre was an object which Rutherford called the nucleus. Orbiting this, like planets, were the electrons. But what on earth was the nucleus? Rutherford was convinced that alchemy had shown him the answer.
To understand how Rutherford did this, we have to get inside his head to think like he did. Rutherford had fantastic intuition, coupled with an intensely practical approach to science. So he hated ideas that relied on complicated mathematics. When it came to the atomic nucleus, Rutherford looked for the simplest idea that worked. And what worked was to imagine that the nucleus is made of tiny, rigid spheres, like snooker balls. Using this incredibly simple image, Rutherford could construct all the elements in the universe. He could explain how the huge variety of different atoms are made of the same basic components. So here's how it works. Hydrogen, which is the simplest element, consists of just one sphere, which Rutherford called a proton, which is the Greek word for first. All the other elements are made by adding more protons to the nucleus. It's as simple as that. So helium, which is the second lightest element, comprises of 2 protons. Lithium has 3. Carbon, which is the element that's the basis of all life, has 6 protons. The oxygen that we breathe has 8. And uranium, which is the heaviest naturally occurring element, has 92 protons. This was Rutherford's inspirational idea, that each element is defined by the number of protons in its nucleus. It's a wonderfully elegant and simple idea, an idea that explains how so much of the universe we see around us is constructed.
But as scientists often find, nature is never quite as simple as it seems at first sight. Sure enough, a big problem emerged with Rutherford's proton. And it was to be one of Rutherford's own protégés who was the first to identify it.
Francis Aston was an interesting character. As a young man, he enjoyed the adventurous outdoors and was into skiing and motor racing. And apparently in about 1909, he discovered surfing off Waikiki Beach in Hawaii. But he soon realised that the call of the physics laboratory was greater than the call of the waves. And it was while at Cambridge that he invented an incredible piece of equipment. That's now housed here in this rather austere and plain-looking building, the Cavendish Laboratory. This is Aston's original spectrograph. It's an amazing piece of equipment because with it, for the first time, scientists were able to weigh individual atoms. It's incredible. It looks a bit like a gun. It's a very strange shape. I guess basically you'd have the atoms that you wanted to weigh in this glass tube, and the electrically charged atoms would be fired in this direction. Round about here there'd be electric plates which would bend those atoms. Because the atoms had electric charge, they'd get bent in the electric field down in this direction. And then what we're not seeing here would have been a huge magnetic coil that would sit around this arm, and the magnet would bend those atoms back up again in this direction. Now, round about here at the end would be a photographic plate. I'm not quite sure if we can see it, no. But the plate would sit here, and atoms of a particular weight would be focused in a line. And so Aston was able to see individual lines for atoms of different weights. It was remarkable that round about just after the First World War, scientists were finally able to weigh atoms.
Now they could weigh atoms accurately. They discovered that there was a fundamental problem with Rutherford's model of the nucleus.
Basically, the numbers didn't quite add up. All the atoms of the known elements, apart from hydrogen, were much heavier than they should be. For instance, helium with 2 protons should weigh twice as much as hydrogen with just 1. In fact, it's 4 times as heavy. Rutherford realised this could mean just one thing. Apart from the proton, there's something else inside the atomic nucleus. But what?
It took 12 years to find the answer. Now, as head of the prestigious Cavendish Laboratory in Cambridge, Rutherford threw all his resources into the project. He bullied and cajoled his students and researchers until one, called James Chadwick, hit the nuclear physics equivalent of gold.
Chadwick built this in 1932, and to think that with just this tiny little piece of equipment, he discovered the missing ingredients of the atom. For me, as a practicing nuclear physicist, this really is an amazing device. When I think of the huge accelerators that are built today to conduct experiments to probe the nucleus of the atom, it's really awe-inspiring in its simplicity, really.
He put a source of radioactivity at this end of the tube, and the radioactivity then struck a small target in the middle here. And then out of the target came new particles that sprayed out of this end here. It's a bit like an atomic gun shooting out Rutherford's missing particles.
What Chadwick discovered was that along with the proton, there's another kind of particle inside the nucleus. It weighs almost exactly the same as a proton, but is much more elusive because it carries no electrical charge. Technically, we say it's electrically neutral, hence its name, the neutron. And it immediately solved the problem of the weight of atoms. So helium is 4 times as heavy as hydrogen because along with its 2 protons, it contains 2 neutrons. And oxygen has 8 neutrons along with its 8 protons, making it 16 times as heavy as hydrogen. So in 1932, the atomic family was complete. Scientists announced that every atom in the universe is made of just 3 basic components: electrons, tiny particles orbiting a nucleus, which in turn is made of protons and neutrons.
Over Christmas 1932, physicists at the other great centre of atomic physics, the Niels Bohr Institute in Copenhagen, celebrated the neutron's discovery and the completion of the nuclear trinity by writing a musical about it.
That which experiment has found, for theory had no part in, is always reckoned more than sound, to put your mind and heart in. Good luck, you heavyweight ersatz, we welcome you with pleasure, but passion ever spins our plot, and Gretchen is my treasure.
Some of the great names in physics took part in this musical. Their excitement was primarily due to one thing. They knew they stood at the threshold of an entirely new kind of science with entirely new rules, what we now call nuclear physics. The first challenge for nuclear physics was this. Although physicists now knew what the tiny nucleus was made of, they couldn't explain how it all held together. In fact, it was worse than that. The existing laws of physics predicted that every atomic nucleus should self-destruct instantly.
The main problem was this. All protons, the key ingredient of the atomic nucleus, have positive electric charge, and things with the same charge repel each other, just like these magnets. Look. So, just like these magnets, if 2 protons get close together, they should then just fly apart. But weirdly, inside the atomic nucleus, they don't. Dozens of protons can stick together alongside each other. So what sticks them together? What stops the protons from flying apart? The answer was big news. It was nothing less than an entirely new force of nature. For centuries, humans had only ever encountered 2 natural forces: gravity, which pulls us down to the Earth, and electromagnetism. But now, hidden inside the atomic nucleus was something completely new. It was called the strong nuclear force. And the easiest way to imagine it is with some Velcro.
If I put Velcro around these magnets, they start to behave slightly differently. At first, they repel each other just as before. But when they get close enough, the Velcro kicks in and they stick.
The effect is very short range, but very, very strong. And it's exactly the same with protons.